necessarily new to you because they are in the same books I gave to you. Just that I chose to extract them from the documents so that you can have them at your fingertips at the time of doing the assignment, at the time of studying. So you might not necessarily have to scroll through the pages in the books, right? These are not new. These are all things that you have before. What I want for you to do is the same thing that we did last week, Tuesday, whereby those with a possibility of downloading them right now and have them open, could you do so? Because we'll be using most, if not all of them, for today's class. In today's class, we're going to be wrapping up on beams. We'll be looking at deflection. And by the way, I did ask you last week, Tuesday, when we were leaving, to look at the deflection aspect of the beam we had done in class as somewhat homework, not gradable, not for grade, but for your own knowledge and as a prerequisite for coming to the class. For those who have done it, would better understand what we're going to be doing today as it relates to deflection. But yes, I want for you to download those bits of material and have them opened so we could go through them. In fact, I'm going to be depending on you guys to be scrolling this morning to go to the different tables which which we will be required to use to do the modifications of the standard stresses from the table. But before we actually get into columns and deflection, I thought it useful to extract this page that I have up on screen right now. The reason being, remember that we said we're going to be limiting our beam design for the course to beams which are restrained against lateral torsional buckling. All right, and that's by doing so, we will limit ourselves to a beam stability factor CL equals 1. That means we do not need to go and calculate CL using the very long and tedious expression which comes into this book. Let me see if I can find it. We want to avoid doing that. I mean, that is something that you should learn, but that can be learned by you either after this or in practice. All right? Like I said, not every, you're not going to learn every single thing in school. You don't have time for that. Your career is for 4 years. Your working life is for over 25 years. So most of what you learn is actually when you start working, because learning never stops. All right. So the the sheet I have on screen right now, which you also have, is the first one I actually extracted last night. It speaks to the rule of thumb method, the rule of thumb method of determining whether your beam stability factor CL is equals 1. All right. And I can assure you that all of what we have been doing in terms of beam and all that you'll be doing in the assessment, which I'll be posting this week, and also your exam, it will come down to one of these cases. And that is why I actually not wait until you having to go and search again. I mean, we have gone through it, I think, in the second class for timber, but I thought it wise to extract it from the book and post it as a separate piece of material so that you can print it, you can have it at your fingertip on your phone, wherever. All right. So it actually speaks to the rule of thumb method, whereby these are the 5 cases that if your beam meets any of these requirements, then that beam will be stable against lateral torsion buckling, and your CL factor, beam stability factor, automatically becomes 1. All right. We don't need necessarily to go through all of them because I mean I think I've done so in the second class. But just for refresher, the first one states that if the depth of the element divided by the breadth of the element is less than or equal to 2, it says no lateral torsion, no lateral support, and no blocking are required. Examples for a 2 by 4 or a 4 by 8 wood member. All right. D in this case is 4, 2 in this case is 2. If you divide 4 by 2, you get 2. It complies with that. Similarly, D in this case is 8, B is 4. If you divide D by B, which is 8 by 4, you get 2. Again, it is within this range. Therefore, no additional lateral support is needed for element of that size. All right. In the same breath, it says if 2 is less than the ratio D over B, and which is also less than or equal to 4, the beam ends are held in position laterally using solid end blocking. Then CL also is 1. So if you would do this check, if you would do this check, and also the beam ends are held in place by blocking, solid blocking. Normally, the question will state that. If you don't get a diagram to show it, then your question will state that. All right. So you're able to do this check to find out. All right. So for argument's sake, our 2 by 8s. Let's check the 2 by 8. D divided by B, 8 divided by 2, that's 4. 2 is less than 4, and it says it should be less than or equal to 4. 4 is equal to 4. So it meets that criteria. So all that needs to happen for that beam to become laterally stable, you just need to put solid blocking at the ends. That's all. So even if it doesn't have a plywood sheeting nailed down to it or screwed down to it right along its length, it doesn't mean that it's not stable. As long as it has that size and has solid blocking at the ends, then it is stable. One might want to ask, what are solid blocking? Solid blocking for timber beams. Okay, fine. So let me find an image. Okay, fine. Are you seeing the image on screen? The one to the right? Class?
Yes, sir.
This one. Okay, fine. So these that run in this direction, the continuous ones, the joists, those are your joists or your beam, really. And blockings are these that come between them to hold them in place. So these are the ends I will refer to as end blocking. So if your 2 by 8 have these are the ends and at the other ends, then it doesn't necessarily need these in the middle to be laterally stable. That's what it's saying, really. You just need them at the ends. Even though they are present right along in this scenario, but we just need them to be at the ends for the 2 by 8s for them to be stable. I'm trying to okay, fine. So like this. So you have two end blockings, this one and this one. So as long as it has these two, for those particular sides that are named out or called out in this scenario, in section in point number 2, then those beams are going to be laterally stable, and it's because of their depth to breadth ratio, really. All right. Similarly, the same thing applies to 4 by 16 and 2 by 6. All right. And again, class, you can read point 3, point 4, and point 5, but please, these are your guide, because not all cases you will be told that the beams are continually laterally braced by the flooring board or the plywood or the ceiling, whatever. No. But something like these might come out in there. And you'll be looking to check these out to see if in fact the beam is laterally restrained. All right. Because if not, then CL is not 1. Okay, for your scenario, you always get CL equal 1, but not necessarily in the form that we always give it to say the beam is laterally braced by a slab or by flooring board or whatever. All right. So have this page, the single page document, right, at your fingertip. All right. The other thing that we are supposed to be looking at now is where we left off. Beam deflection, the limits, and how we calculate it, right? Without even reading, I find. So you also have this document in your Google Classroom. I gave it the title Beam Deflection Check and the Limits. So you can have that one also ready right now at your fingertips. Without even going through all this narrative at 4.1.3.3. I just want to jump straight into looking at these scenarios. Last week, Tuesday, I did say that there are tables, including the tables that are given to you in your exam, that will have different cases of beam types and formulas to find the maximum deflection. All right. Here we have a few of them. The first one, the first one is a simple supported beam. The case that we are with uniform distributed load, the case that we are more familiar with, and below it are the shapes of the shear force diagram and the moment diagram. And yes, class, the US also shows the moment diagram sometimes like this, inverted. We are accustomed to see it down here, but it can go up there. What is important is that you know what it means and what the maximum value is. All right? Not because it's up here doesn't mean that the formula changes. No, it's just a matter of representation. All right. So yes, so the first case is for a simple supported beam with uniformly distributed load. All right. The second case, same simple supported beam, but this time with a point load or a concentrated load in the middle of the span. And again, this is the shear force diagram for it. And this is the moment diagram for it. I'm not too sure if the shear force diagram is correct though. Should be looking like this. And with the value of the load at the middle, shear force diagram should look like that really. So books do have errors. Shear force diagram should actually look like that, and not what they have there. You see what this look? It should look like similarly. It should look like this. So that's an error on the part of the book. But you can verify that if you want. Let me get one for you quickly. Shear force of simple beam with point load in middle. Okay, see there. So this is what the shear force diagram should look like. So the book actually has it wrong. All right. So find a way to sketch this properly. In fact, let me do that for you. Should actually do this. It should look like this. Yeah, this is the diagram should look like, and not what they add. All right. All right. Now the third case is when you have the same simple supported beam with 2 point loads. Those point loads, class, are at 1/3 points, meaning from this end to this end, from this end for the first load is 1/3 of L. From from the first support to the second load is 2/3 of L. Or similarly, from the from the right support is 1/3. So it's 1/3, 1/3, 1/3. All right. And the moment diagram should the shear force diagram should look like this, and moment diagram look like this. Now, there's hardly a case where you are forced to look at something like this, but of course, these kind of beams do exist. All right. It depends on what your beam what your beam is doing. This may be supporting two other beams which are resting like that. All right. The fourth scenario is when you have a cantilever, meaning a beam with one support only, a rigid support right here at the left, and then this beam is just hanging off to it. That means you have maximum moment, and maximum shear at the support, which is what these are actually saying. That's a cantilever beam with a uniformly distributed load. All right. You also have the same cantilever beam with a point load at the extreme end, at the free end. And this time this is correct. This is what the shear force diagram should look like. So they had actually given the shear force diagram for this up top. All right. Now, class, with these cases, you for the most part will be stuck in the maybe the first the first 2 or 3 cases, simpler cases. There are corresponding there's a corresponding table that shows the formula for shear force maximum, maximum moment, and for your maximum deflection. We are already accustomed to these two: maximum moment and shear force for simple supported beam with uniformly distributed load. We've been doing that for steel, and timber. All right. So the first case we all know, these two. The only thing that we haven't used before is the maximum deflection, which is this one, which is 5, the maximum deflection, delta, is 5 times the load times L to the 4th power, which is the span of the beam, over 384 EI. E being the modulus of elasticity. In this case, timber has two, one for bending, one for deflection. So it's one for deflection in this case. And I is the moment of inertia. Last week, we looked at moment of inertia. We are doing simple rectangular beams or square beams. It is BD cube over 12. We have gone through that. I is BD cube over 12. And that comes out in inch to the 4th power. All right. So we are, for the most part, in this particular scenario. For those who attempted to do the little homework to find the deflection of the beam, you would have been using this, or you would have used this. Right? And similarly, all the other cases have their respective shear, maximum moment, and maximum deflection formulas. All right. For those who are interested in the others, because we are actually stuck at this case for now. All right. Now, let's look at the limit. So we know that we'll be using this, but there what why are we calculating deflection? Because we now need to know if the beam meets deflection criteria. Now, the next table, class, is this one, table 4.2, is the deflection limits for framing members. Framing mean beams, right? Whether they want to be joists, girder, beams, purlins, lat, whatever you want to call it. As long as it's a beam, it's referred to as a framing member. All right. Now these are the deflection limits. Let's look through this table, all right, and see if we can understand. So the first part is the member description, where the member applies. All right. So we have two things really. Timber beams can either be in roofs or in floors. All right. For roofs, when it is supporting plaster ceiling, the maximum allowable deflection for live load only should be the length divided by 360. Right? The 360 is a number. The length is in unit of length, so it comes out in feet or inches. Right? For the same member supporting plaster ceiling, if snow or wind is applied, then the maximum deflection should be the same L over 360. All right. So this is live load alone. This is snow or wind alone. Now, for the total deflection, that's when you're adding dead plus live. So it's dead plus live. Then the allowable deflection is L over 240, which is a smaller deflection really. A larger deflection really. This is larger. Because the denominator is smaller, that means it's a larger value. And it's because you have a combination of loads now. So it allows for more deflection. All right. What should happen, class, is that same element, the deflection should be checked for both live alone and a combination of loads. And it should satisfy both scenarios. It can satisfy the live load deflection limit and then not satisfy this, and we say it's satisfactory. No, it has to satisfy both or all three, if all three are involved. I said both because we're not going to be looking at this wind and the snow scenario. So we'll be looking at floor load, live load, or roof live load, and dead load. So it must satisfy the live load criteria and the combined load criteria. All right. Similarly, for roof members supporting non-plaster ceilings, all right, then you have these criteria, and they allow for more. They allow for more because these are non-plaster. That means they're not all that brittle. So more deflection is allowed because you're not expecting to crack or even break. When it comes on to plaster ceiling, like gypsum board, those are all plaster. Those are referred to as brittle. They can break. So you don't want them to be deflecting and moving too much because it will crack up and break up. Right? Which is why these limits are much more rigid. The permissible is much lower than the permissible down here. All right? And look at these now. For say a roof member not supporting a ceiling, that means those roof members are just there by themselves, only carrying the roof, no ceiling below. They are actually allowed to deflect even more because nothing depends on them for support. All right. Now for floor members, the ones which we are mainly looking at for the most part, and it says all members. It doesn't matter if you want to support ceiling, tile, gypsum, ply, whatever. All of them should meet these requirements. For live load alone, L over 360. For snow or wind, the same L over 360. And for dead plus live, L over 240. So it's similar to the first case up there. All right. That's what those are what we refer to as limits. So when we use this formula class, this expression, to find the deflection of a beam using live load only and live plus dead, then what we do is to now check if those deflections based on the loads acting, if they are greater than or less than these values. If they are less than this value, then fine. If they are greater than the value that comes out from here, then the member is no good. It fails under deflection. It's going to be deflecting excessively. And that requires maybe spacing the members closer or using a deeper member. That's what really happened. When a beam is not satisfactory under deflection, you can either bring them closer so you get less loads, or if you want to keep the same spacing, you have to increase the depth. And that way, the deflection becomes lower. Or we can double them. We can double the timber members, put two beside each other. All right, but that's already done in Jamaica. We don't have the kind of economy for that. So we prefer to increase the size a bit or space them a bit closer. There's much more economic gain there. All right, class? All right?
Yes, sir.
All right, so it says here, there's an alternative method of calculating deflection, and that is really to use the required moment of inertia. We won't be getting into all that. We want to use the basic formula to check your deflection. All right? So these come down to these two. Check of deflection. Using the appropriate deflection formulas, determine and compare the live load and the total load deflections to the appropriate deflection limits. For a uniformly loaded beam or girder, we obtain live load deflection, right? And they call it deflection LL is equals to 5 WLL over that, right? And it should be less than that. Like I said upstairs, it should be less than this, all right? And total deflection, it says including creep, it should be this. It's called delta K, and it says it's dead load plus live load, which is this, and it should be less than that. It means you have to add the loads first before bringing them inside here. All right. Where E prime, modulus of elasticity, is the E you take from the table times the Cm, right, times Ct times Ci, and we all know what these are, right? And the stress adjustment factors are discussed previously. And it says there's a value K, there's a value K which applies to them, and that K is a creep effect. Because it did say including creep. Creep class is when a member tries to get shorter. It creeps, it gets shorter. And it happens to concrete, it happens to timber. It doesn't necessarily happen to your steel beams. They don't creep. Maybe they have a bit of creeping during the manufacturing of the steel when it's in the drying process. But after that, it doesn't creep. But timber and concrete do creep. They shrink. Creeping is a form of shrinking. It affects the geometry, the length especially. All right. So there are some factors which are a factor K which comes into effect. And it says K equals 1 for green or unseasoned lumber. We don't use green lumber out here. We get them when they're seasoned and treated and sent from South America or wherever we get them from. K is also equal to 1 for seasoned lumber using wet service conditions. So if your condition is wet, then your K is going to be 1. And it's 0.5 for seasoned or dry lumber or glulam in dry conditions. All right? So we can have either the second or the third case. We don't have the first case because we don't use green lumber in Jamaica. But we can either be in the wet service condition, whereby K equals 1, or the dry service condition, where K is equal to 0.5 for any lumber. Dry lumber, glue laminated lumber, or prefabricated. We're not using prefabricated. All right? L is the span of the joist, the beam, or the girder in inches. All right? So you put them in inches. So you can get the result in inches. And the deflection, K, total deflection, is due to the total load, K times D plus L, or LR plus I. Fine. So the combination now could be dead plus live in the case of floor, dead plus roof live in the case of roof, or dead plus snow in the case of snow. All right? That's total deflection. The deflection due to live load, is going to be either floor live, roof live, or snow live. In our case, we're doing floor beams. We're going to have floor live, occupancy live load. All right. And to find your WK, which is the total load when you combine live plus dead, you have to put again apply the K value. The K value actually is a reduction value for your dead load. All right, it's a reduction factor for your dead load. You only reduce the dead load in that case because not they're saying that not all of the dead load will be contributing to deflection. All right. All right. So that is how we actually should check your deflection. All right. For both live alone and live plus dead, a combined load. All right. Applying the necessary factor to reduce the dead load. To determine the maximum allowable load that can be supported by I-fine. So we can actually use deflection. We can actually have a beam geometry already. The length of a beam, the size of a beam, and we can use deflection, the deflection criteria to actually calculate the maximum load it can carry. That's really the reverse of getting a beam with a load and check its deflection. We can actually say, okay, fine. I I have this beam. Let me see the maximum load it can be designed to carry. And that's really doing the reverse. It's really the reverse process is done here. We're not going to be going into that scenario because we're not going to be getting that case. All right? We're going to be designing beams, or we're going to be putting beams to analyze it, not to find the load that a beam can carry. All right? Now, so for what we have done last week, the example we did last week, anybody did manage to do the deflection for that particular beam? Anyone? I want to share it with us. Class? Class? Hang on. Class?
No, sir, I didn't do it.
What didn't do it? Apart from
Sir, I did it, but I'm searching for it. So.
you did it, but you're searching. All right, fine. Search and find it fast. Can I allow people to share their screen in this Google Classroom thing? How it works?
You can, sir, but
Sir, we can share.
You can. Without me giving permission?
yes, sir.
Oh, that's fine. Because in that case, you'll share what you have. If I want to find it. So I can close beam stability factor. In an event, if we don't find it, then we'll be doing an example really where we're going to be checking the deflection. Right. I've come with a prepared example where we can check the deflection. Still don't find it?
No, sir. I'm searching in the book, sir. But
All right, no
Google
problem.
has it for one, but-
No problem, no problem. Let's look at this work example quickly. So we can, because after doing this example, and we would have wrapped up beam really. Right? It's a relatively short example. More, more, more like what you get on your assignment and your test, your exam, sorry. All right. Just that in these books, it's difficult to find examples with floor beams. They can talk about roof, American thing. All right. The example, you also have this example. Hopefully you download it. All right. But I give it the title Beam Design Example. All right. So you got that last night. It says here, design roof rafters spanning 16 feet. That means the length of the rafter is 16 feet and spaced at 16 inches. So the spacing is 16 inches apart on centers. All right. OC means on centers. All right. The plywood roof sheathing prevents local buckling. All right. Therefore, it means that plywood roof sheeting are nailed down or screwed down to these rafters, and those provide continuous restraint at the top edge. Hence, it eliminates the whole effect of lateral, torsional, or local buckling. All right. The dead load is 12 pounds per square foot, and the roof live load is 20 pounds per square foot. All right, class. Let me say something here. For those who are actually interested in learning and want to do as much independent study and practice as possible, especially for your exam. Even though this says a roof beam right now, because I mean that's what we lecturers do when we set an exam. We find an example and change things about it. So we're going to be doing this as a roof thing right now. It doesn't mean though that you cannot create your own scenario from it. As a second question to get practice, you can now change this to a floor beam and put on floor loads on there. You can also change the type of timber, the species of timber. It's saying right now it's saying Douglas fir larch. You can now go for a southern pine or some other thing, cedar, aspen, just to have different values so you can now learn to use the tables. All right. So that's just something that I figure out, point out, because I mean that's what we do. Take an example and say, okay, fine, let me create a different scenario from this, as opposed to give it back. Because I know that some students do that. The moment you see a question, you type it in Google, and you might very well find the answer. So we know that. So we say, okay, let's change things about it so that you can type it and you'll find. So you can actually type this in Google and find it. The answers for it. I guarantee you that. because it's a long-term literature. Anyways, let's continue. So here we have a roof beam, a rafter, 16 feet long and spaced at 16 inches apart. It carries two loads really, the dead load and the roof live load. Give God thanks there's no snow. All right. The timber is Douglas fir larch. All right. Now let's start by calculating forces. All right. Who's that? No, Darren Morgan. Let's start by calculating forces. Tributary area, right? The tributary area is calculated as 16 divided by 12. Why 16 divided by 12, class? Times 1. And let me see if I can draw a representation of what that thing would be.
Here, the 16 divided by 12 is to convert it to feet.
Huh?
16 divided by 12 is to convert it to feet.
Yeah, but which are the 16? We have two 16 there. Which are the 16 divided by 12?
The inch, sir.
The spacing, the 16 inches. Good. All right, so I can get rid of it. Okay, fine. So this first 16 class is converting the inches into feet, because everything is pound per square foot, right? I want to go in the table. All right, so they convert this into feet, really. All right. And times 1 is by 1 foot. right? And that's what they get the foot square from, per foot. All right. Now what they're going to do now is to calculate the loads per foot or per feet. All right. So for your dead load, they give you the value as 12 pounds per square foot. If you multiply by the tributary length, then that would give you the linear load on the rafter itself. So the dead load converts to 16 pounds per foot on the beam. Similarly, your live load carried onto the beam as a linear distributed load is 26.66 pounds per foot. So what we have is a beam now looking like this. And I'm going to make a sketch looking like this. That's a beam. That's your support. This beam is 16 feet long. 16 feet. You can quickly make your sketch as I go along. That's 16 feet long. And we now have all right, so let's copy these up over there. Let's flatten that. We don't want that. So what we have is that. Okay, fine. So we have that as dead load up there. We don't want this. And we also need a live load. And let me see if I can do it faster by taking this alone. And by taking this alone from the equal sign. And if I should make a group with these, I cannot drag them. All right, fine. So what we have is this. All right, fine. So that's our beam class. Everybody have that? Make that quickly. That's what we have as a beam. All right. It's Douglas fir larch number 1. So this is also important. It's Douglas fir this, because we'll be going into the table with this. They haven't given any climatic conditions, so we're going to assume that they're going to be looking at dry, normal condition. After all, it's a roof. All right, fine. So this is also important. All right, so these are now. All right. Let's save that. Everybody follow up to that point?
Yes, sir.
Okay, fine. Now, this example gone straight into the LRFD. All right? Because look at the combinations. All right? So right away, by looking at them, we know that this is LRFD. All right? LRFD. Because the 1.6 and 1.2, those indicators, those are LRFD combinations. All right? So I put in beside it, that is LRFD. All right? And that's 1.2 dead load plus 1.6 live load. All right? And it comes out to be this. All right? And hence, using the formula for maximum moment, WL squared over 8, right? This L this time though class is the feet, the length of the rafter, 16 feet. All right? And it comes out as 1974.52 pound foot or 23.75 kip, inch kip. All right. I take it I don't need to tell you how to convert from pound foot to inch kip. We already know that 12 inches make 1 foot and 1,000 pounds equal 1 kip. So with those basic units in mind, you can move from this to this. All right. Similarly, we calculate the maximum shear force. It's a simple supported beam with uniform distributed loads. So using up what we looked at this morning, using up this expression, then they arrive at this. All right. So these are all not new to us. We know that from analysis class. All right. Now let's look at the tables. What do we need to get in the table for? All right. We're going to look at reference design values. All right. So we're going to the National Design Standard, NDS, supplement, this one. And we're going to look for design values for bending and for shear and for compression and for and whatever else that we might need. All right. And that is when your species and your size become important. What tables were those in again? We used them last week. Okay, fine. Here we are. All right. Now, what do we go into the tables with? When it's Douglas fir, number 1. Douglas fir large, number 1. All right. They did not give us any size because we are asked to design them. So we can assume one size to go in the table with. You can always assume and say, okay, fine, I'm going to go in there. I'm going to use a 2 inches thick lumber. It's a roof lumber. So that's what you normally start with, nothing less than 2 inches. And that is why they have gone in the table with 2 inch and wider. It wasn't given. No way up there, it wasn't given. But if you're going to design something, you are the engineer have to fix some things. So you can fix your thickness. So they have fixed the 2 inches. All right. So they go into the table, Douglas fir large, 2 inches. All right. So we go into the table, look for Douglas. Right, so we're looking for graded lumber, 2 inches thick, 2 inches to 4 inches thick. So in the right table, I'm looking for Douglas fir large, number 1. So the table just starts. There's no Douglas fir large yet. Okay, fine. So see, Douglas fir large and number 1. This one. All right, number 1, 2 inch and wider. So anything in this 1, 2, 3, anything in this third row, we want to be taken out. So the first one is FB, bending. That's 1,000. Let's look. FB, 1,000 PSI. All right. They have taken out shear, FV. Same Douglas fir large. FV is a third because they're not looking at tension. We'll move to shear. So FV for Douglas fir large, number 1 is 180. See there? 180. All right, we'll be following because that's what you'll be doing for your assignment plus your exam. So that 180 comes from that. And they take out, because we're going to check deflection, they take out the module of elasticity for deflection, and this also comes in for bending, so we take it out. So we take out both moduli of elasticity, E and E min. So let's go back. For the same element, Douglas fir large, number 1, and those E's come as the 2 last step, penultimate, the 2 second to last. All right. So again, we're back here and we go. So it's 1.7 million. 1.7 million plus 620,000. All right. So let's give up to our example. See there? 1.7, right? Plus that. All right. So these values class, we know where to get them from. It's a matter of using the species and the size timber. Again, the size was not given up here because the thing says design. It didn't say analyze, it said design. That means we are asked to find this to make a size for it. All right. So we have to start with something. We can start by the width of the element. All right. Because the table do speak to the width of the element. All right. And we take out the reference values, reference design values, which we did right here. All right. So the next thing right here, according to this, is the preliminary design. Initial adjusted bending design values. All right. Now, these values, resistance value, reference value for bending, lambda, which is the time factor, KF, and CR. How do we arrive at those, class? Again, we have to find them in the literature. Under the LRFD. We have gone through that last week. Do we need to go over them for this exercise?
No,
Class?
sir.
No? I wouldn't mind, don't have to. Huh? Yes. All right. So one person said yes. All right, fine. So we're using the LRFD method. In the LRFD method, there are 3 factors that only come in the LRFD method. This one, phi at the front of it, is called resistance factor. Lambda, time effect factor. And KF is called a conversion factor. KF, conversion factor, is really to convert these values from ASD to LRFD. Remember that the timber design, American Design Code, was developed only for ASD method up to the year 2005. After 2005, they decided, okay, we want to do LRFD design for timber also, just like concrete and steel. So they did the quick thing of saying, okay, fine, let's convert the ASD to LRFD by applying a KF, which is a conversion factor. Now, everything else in here, apart from KF, lambda, and phi, everything else in here would be applicable even under the ASD. This FB, which is the reference value, and the CR. All right. Now let's look back at what KF, lambda, and phi values are for the given scenario. It takes us back to this page. Before each table with the reference values comes the relevant factors. Right? CR is repetitive member factor. Why? It's repetitive because the elements are spaced less than 2 feet apart. If you read this narrative, it says for bending design values FB, for dimension lumber 2 inches to 4 inches thick, we are in that because we have chosen 2 inches thick. Shall be multiplied by a repetitive number CR equal 1.15. When such members are used as joists, truss cores, rafters, studs, planking, decking, or similar members which are in contact, not our case, not in contact, or are spaced not more than 24 inches. All right. In our case, whoever happened to go over it, our spacing is at 16 inches, so it's less than 2 feet. So already we meet 2 criteria. The element size is 2 inches thick, so it's within this range, and they are less than 2 feet apart. That means CR equal 1.15 for us. So if we look back at the example, CR right here, see there, 1.15. So we know where that comes from now, right? That belongs to that. So we're clear on that. Let's go to KF. We're doing them from back coming from. Let's go to KF. Our KF value, not on this page, but KF value will come all the way up to the top of the table, the page or the book. Let's go all the way up. KF would come all the way up, which is why I was hoping not having to go through all that. But let's see if we can find KF and we arrive at KF. I have a feeling it's all the way up, further up, further up. I did last week though. Highlight all the pages that those values come on, right? Remember, class? Class. Last week, Tuesday morning, we spent the time and highlight the pages in the books that we're going to find these tables. Anybody have that recorded? Where exactly find KF again? Maybe not in this table. Let me go to the NDS, because we're using both NDS and the supplement to the NDS, and some things are quicker to be found in the what is it? Right, fine. We're looking for KF. Okay, fine. So here. Okay, fine. So we're looking for KF value, and see it says it here, LRFD only. Members. So the KF table is relatively simple. It's for a member or for connections. We're not doing connections, we're doing members, and we're looking for KF applied to the bend stress, which is the first one, FB. That's 2.54. All right, so KF is 2.54. See there, 2.54. All right, so we know it. So we already found where those two values come from. All right, lambda, which is your time dependent factor. Also, we can find it. All right, so not up here. We can find phi. Let's look for the phi value. See that we're on the same page right there. We have to find lambda elsewhere. Phi. Again, this table, it deals with members and connections. We are not doing connections. We are on members, and we have to look for it depending on the stress you want to apply to. We want to apply to the bending stress FB. So lambda is 0.85. If it was for shear stress, FV, it would be 0.75. So we're going for bending, it's 0.85. So we know where this 0.85 comes from. It's for this. So the only thing we're missing out now is lambda, which comes on a different table. Lambda, on a different table. I was hoping that someone could remember quickly what tables those are. But we'll get back to that. Lambda is time dependent factor, and it depends on the load types. Right? It's a factor that modifies CT. It's a time factor. All right? But for this case, let's say it's 0.8 in the interest of time. Somebody say something? Because I really want to do this and so we can move to columns. All right, fine. So lambda is 0.8. That can be verified after. What I might have to do is to crop out those tables like I do with everything else and send to you guys individually. But I wanted to avoid laziness that people say, boy, they book them to have scrolling, because that's what I have to do anyways, to crop them out. Anyway, so let's say lambda is 0.8 as they have there. The modified bending stress would work out to be 1986, up from 1000. All right, and that's PSI. Now, because it's a design and not a analysis, they are now calculating the required modulus of elasticity. Based on what we know, is that the moment times the moment times modulus of elasticity is equals to the moment times section modulus should be less than or equal to the stress, which is the bottom one. So it's a matter of rearranging the equation. All right. To say, okay, fine, let me use the moment I have from the loads and the stress I have estimated to find a required section modulus. And from this section modulus, I can now find my depth because I have already assumed the width of the element. All right. So that's what happens right here. The moment you know because you calculate it from up here, that's acting. Multiply by 1,000 because you carry to foot pound, and then you divide it by the estimated stress based on the material for the timber. All right, which is this, and it gives you a section modulus of 11.96. What unit is this, class? 11.96 what? This is inch cube because that's S. It's B D BD cube over 12 divided by C, just so BD square over 6. All right, and it's 11.96. So what they do now is to go in the table and try different sizes, right? Or try a size that is just above this. So they said try a 2x8 of the same Douglas fir large. Bear that in mind. You can't at this point change the timber species because this value, this 1,000, all of this was chosen from a Douglas fir large. So you can't all of a sudden change the element now and say, okay, fine, I'm going for a cedar one or a pine now. No. This is bearing in mind the same Douglas fir large. All that happened is that you will now use this with everything else you know to come up with a depth. Right? So they are saying try a 2x8 inch Douglas fir number 1 large. That will give me a section modulus of this, which is greater than this. So I can now go back and confirm my design. That's what they did actually. So they're actually going now and do a revision of all the reference values. So these reference values from the table remain because it's only dependent on the species and the thickness. It's Douglas fir large number 1, 2 inches thick. The 8 inches doesn't come into play yet. All right, and all I do now is to re-look at the reference values. 0.85 doesn't change. It can't change because that's the phi value for member on the bending. Lambda remains the same. The conversion factor remains the same. It's a conversion factor for bending. CF and CR. Now CF comes into play. Let's remind ourselves what is CF. Let's remind ourselves what is CF. Size factor. All right, so this is CF. The size factor, class, because we know the size, we can now know what the size factor is for bending. So you have bending, tension, and compression. We are in number 1. This speaks to number 1 and number 2. So it says select these grades apply. All of these grades apply. And we have to look at the width. All right, so we are in the 2 inch. We're in the 8 inch rather. This is the width. We're in the 8 inch. And we're under the 2 inch column. So we are in this. So we're doing for bending, and this is thickness. We're in the 2 inch and 3 inch. We're also 2 inch. We're in this column, and our width we have chosen 8 inches. Right. So 8 inches and 2 inches, and that is pointing to a CF value of 1.2. Let's see what they have in their let's see. They have a CF value of 1.2. CR value was already 1.1 because it's a repetitive number value and it's less than 2 feet apart. And we have already decided on that from all the way up. So this is the only thing that comes in new now. And it comes in new because we actually confirm the size of our element to be 8 inches deep. That's why it's going to come in. It's a size factor. Right? And with that now, these are now the confirmed or the adjusted bending stress value, this value. Similarly, we look at the shear value, and these are the adjustment factors for the shear. Is 0.75 for the shear, which I had pointed out earlier when I was looking at the first tables. I want to quickly go back to it. All right, fine. So CF for shear, FV, see there? No, phi for shear, FV, see there? 0.75. And KF for shear is 2.88. So it's 0.75 and 2.88. Let's verify that. 0.75 and 2.88. And this lambda remain the same. So with that, you have an adjusted shear stress of 311 psi. Nothing modifies there. E prime and E min is modified by these two. Right? Whenever you see a dash, it means there are no modification factors for those. All right. So we can now check the bending strength of the element using the bending stress from up here that we modified, and also the true modulus of elasticity. Sorry, the true modulus of section modulus. Are you following, class? Class? Class?
Yes, sir. Following. Yes, sir.
This part we did this part we did last week. Because our example last week would have given us a size already, 2 by 8 or 2 by 12 or 2 by whatever. Just that this example actually asks us to design it, so we have to size it first. So this part of it is really new, not new, but required of us to come up with. All right. But from this point down, we'd have done the bending stress check last week. As a matter of comparing now the stress that the capacity stress versus the moment. This is really finding the bending capacity in form of moment. All right, because it's the moment. So your moment capacity is more than your moment load or your moment from your loads. That means that in bending the beam is okay. And they do the same thing for your shear. Last week we look at the shear stress, and we remember this formula 2 over 3 VA, 2 over 3 A. But this time it's using the shear strength and not the stresses. So it's the stress times 2/3 of the area. We'll give it this shear itself in kips. And this is what is done right here. So the area is 10.88 square inches. We already have the modified shear strength, which is up from the table up there, 3.11 psi. Sorry, 311 psi. And the 2/3 is really a factor coming from the formula that we have developed last week. And that gives you a shear strength, horizontal shear strength really, of 2,255 pounds as against 494 pounds. Or from up here. All right. Ultimately, and that's what you do for beams really. Check moment, check shear, and check deflection. Ultimately, this is where we want to get, because this is what has been missing from what we did last week. Check for deflection. So again, class, we have to check deflection for two things. For the live load only and for the combined load. This is a roof, so they're checking rafter. So this is going to be a bit different from what you will do if you're doing a floor beam, and that is because the criteria for roof is different from that for floors. See there? It's a roof, so you'll be checking, well, it's the same thing really, internal factors, but all of them are to come to this table. You'll be checking the for live load alone, and that should be less than L over 360. And if you combine it and live, it should be less than L over 240. All right? But for roof, it depends on three things. If it's supporting a plaster ceiling, if it's supporting a non-plaster ceiling, or if it's not supporting a ceiling. So let's see what scenario they work the example to be in. All right, so for the deflection check for service load, this is for the combined service load now. Note, for deflection, the load shall not have any combination factor. It's service load. So it's the 16 as a dead load as calculated from up here, and the 26.66 as live load, as they are. All right. And that is 42.66 pound per foot. Put that in the formula. That's what they did right there. And that comes out to 0.78 inch. That 0.78 inch, they are going to check. Okay, and they are saying that their ceiling, it doesn't have any plastered ceiling. So if it doesn't have any plastered ceiling, they are in this range. They are checking the combined load. So their requirement is really L divided by 180, which is this. All right. So L is 16 feet converted to inches by multiplied by 12 divided by 180, and that the maximum deflection they should have for the total load is really 1.07 inches. Yours is, or ours is 0.78, which is less than that. That beam is okay. They did not do the check for the live load alone, but we can do that. If we check the live load alone, class, we will be looking at this scenario, but over 240. Over 240. Now, why didn't they do it over 240? Because this one is going to be less. But let's look at the 240 one with 1 over 240. Let's look at the live load by itself for calculation purposes and for practice purposes. Somebody please put in the live load, the 26.66 into this formula and tell me what you get. Please, quickly. I want someone to do the live load by putting 26.66 in this expression. While you do that, I will prepare for the response. We're doing for live load only. So what we want is this. And we want to now start to change up what this looks like. Somebody doing it?
Yes, sir, doing it.
You're doing it? Okay. Okay, fine. So already we need to change this 42.66 to 26.66. 26.66. Fine. So this comes right here.
0.
So that's the only thing that changes. Huh?
There's 0.490.
0.49. It works out to be, let me do that now. equals to, well,
49.
0.49, and that's inch. 0.49 inch. What shall we compare it against now? That should be compared against L over. Let me look for it now. Right, so 0.49 inch, and that should be compared against. It's not supporting anything. No plus. So we're in this case really. I will give a live load only. Right. So it's L over 140 over 240. So we should know that's the scenario. So what I want now is L over 240. So let's do the L over 240 thing. So we want to make a copy of this one.
0.8.
All right. So I put this down here, and I want to flatten that because this now becomes 240, right? Down here becomes 240. All right. And you say that this becomes what was the answer?
0.8 inches.
0.8. 0.8. Okay, fine. So for live load alone, we are allowed to have a deflection of up to 0.8 inch. All right. And what did we get? We have something which is less than 0.8, don't it? So it is greater than 0.4. Okay. So at the end, we can write greater than 0.49 inch. In bracket, we put OK. That's it. That's what it's really about, really. And this is for all of this down here is for live load. So let me put up here live load deflection. Check. That's live load. All right. So for those who are making your notes, make your notes like that. The first one is service loads, which you could put beside it. Is really the total deflection. It's called total deflection. Total deflection. They have not used the creep scenario in this. Where to look at creep? What creep would have? What the creep value would have been? What's season number? Would have been 0.5. But they did not look at creep in this scenario. All right. But this part of the class that we just did at the bottom here, down here, is what we were missing last week. I just didn't want to do it by itself. I just wanted for us to see how a complete beam design or analysis is done. It's moment, shear, deflection. Huh? Why? Like I said before, one can be okay and the other don't have to be. Yeah, right, so right, let's check it. Not because the total is okay doesn't mean that the live will be okay. Understand? It's just work out this time though that the live is okay. But there are scenarios where one is okay and the other is not. And it doesn't have to be live. It could be the total not okay while the live is okay. Right? It depends on the load. Right? But the correct thing to do is to check both of them. Apart from the question, everything is clear? Everything is clear? I'm giving you some time to write off and to finish, capture that. I didn't want to write it off or take a picture of it. I don't know. because we're going to be moving on to column. But before we move to column, in the material I sent last night, I also sent a work. It's called worked example of a beam of beam. There's this example, which also goes through the whole analysis of everything, very long, and also quoting the tables which you're going to be using to find whatever, and it goes all the way down. All right. So that also can be used as a practice. All right. With this class, we would have finished what we're looking at with beams. So the only thing for you to do now is to do your assignment, which I'm going to be posting this week, and use everything I have now to prepare for your exam. All right. So this is where beam finishes really. Like I said before, nothing prevents you, class, from creating your own scenario. You can change things about this. You can change the length. You can change the spacing. As long as you keep it within 24 inches or 2 feet, so that your repetitive value is 1.15, or whatever the case may be. I mean, it doesn't mean you have to keep it within that. But you can change up the material, the species rather, from Douglas fir larch to maybe southern pine, to aspen, to cedar, to Douglas fir, something else. We have multiple timber type which you can use. We have Alaska cedar. Within that you have number 1, number 2, number 3. So you can change from number 1 to number 2. You can change to select structure. You can change to stud. You can do so much things to create several work examples from just the one or the 2 examples that we have done so far. You can change the load. All right. So don't limit yourself to just look back over what we did in class. Get some practice for yourself in terms of having to use the tables and whatever we have to use by creating scenario which force you to move away from just going back over the example itself as it stands. All right. So we can move to columns now.
Yes, sir.
Sure. All right. So I'm going to close out all these. All right. So we'll finish with beam deflection. Save that. We're going to keep that. We're going to keep this open. Keep that open because we need them. Okay, fine. Now we're going to be looking at columns, and within columns now. So we look at column work example. That's that, and compression member. All right, fine. So columns should be relatively small, short, because there's no deflection on integrated columns. All right. Don't want to start with that. Here we'll have critical formula. Here we'll have critical buckling stress. Here we'll have critical buckling stress. All right. So okay, fine. So among the documents I sent last night, also there is one called compression member design. All right, that's columns really. Well, compression means columns and struts, because you can have members in a truss, which are also compression, which are not necessarily columns. And the same principle applies. All right. What we're looking at, class, is pure axial compression. All right. It's called pure axial because the element is subjected to just axial force alone, no axial plus bending. Similar to what we did in steel design. Because of course we know that we can have a column subjected to axial plus bending at the same time. All right. We're not looking at those combined scenarios. We're looking at the simple ones. All right. It says here there are 2 categories of column: solid columns and built-up columns. I beg to tell you from now, we're looking at solid columns from solid lumber. We're not in Jamaica. We're not into the whole timber construction so much more to go and use built-up columns. Built-up columns mean when you use boards and nail them up and form a box. No, we're just into buying a 2x2 a 4x4, a 6x6, or a 8x8, and make a column. All right. Examples of solid columns include interior building columns, struts such as trench shores, studs such as wall studs when we do dry walls and panel walls, and truss members. Built up columns are made up of individual laminations joined mechanically. All right, so like I said, we're not interested in that with no space between lamination. The mechanical connection between laminations is made up of bolts. I find. So that's just for us. That's just for knowledge purpose, but not because we're going to get into it. All right. The strength. So we can jump over the bottom part of that. Right. The strength of a column is affected by buckling. This we know from concrete design. This we compounded even more when we did steel design last month. All right. If the column length is excessive, because we know that buckling is in function of its length and its effective length based on its end conditions. So we're going to be going right back into those. There are two types of columns with respect to column length. We have short columns and long columns. A short column is one in which the axial strength depends only on the crushing of the material capacity of the wood. Similarly, it would have been the crushing of the concrete. Similarly, it would have been the yielding of the steel. Right? So with timber, short columns will fail if the compression strength of the wood material fails. A long column is one in which buckling occurs before column reaches the crushing of material capacity. All right. So for long columns, a small load can fail the column because it buckles, not crush. It takes a small load to buckle and to crush. All right. The strength of a long column is a function of the slenderness ratio, KEL over R. We already know this. K, the effective length factor, LE, L being the length, and R being the radius of gyration in that particular axis. Remember, we have two axes for regular rectangular or square elements, symmetric elements. We have the X and Y axis, and R is the radius of gyration in whatever axis. Bearing in mind that we have to check the slenderness in both axes. All right? Unless you can look at the element and decide which of them is weak or which of them is strong. If you have a square element, both elements are the same, both axes are the same. Like if you have a 4x4 column or a 6x6 column, if there are no intermediate supports along any of the axes, then both axes will be the same. So you might just need to just check one. However, if you have a rectangular cross-section column, one axis is going to be stronger than the other. We check the weak axis, unless, of course, again, unless we have some internal bracing in the weak axis, which can also cause that axis not to become stronger than the original weak strong axis. All right, so it depends on the geometry which you are given. All right, but just remember, we have to check slenderness. All right. Okay, fine. The radius of gyration is given as for a normal, regular, square, or rectangle. The radius of gyration is given by this. The root of, or the square root of, I over A, where I is the moment of inertia of the column member about the axis of buckling. So if we check in Rx, you're going to be using Ix. If we check in Ry, you're going to be using Iy. That's what this is saying. I is the moment of inertia of the column member about the axis of buckling. A doesn't change. There's no Ax or Ay. The area of the column is the area of the column. All right? The allowable stress design equation for ASD method and the interaction equation for the LRFD method for this pure compression load case are given as follows. All right. So these are the stress. For ASD, is small fc is equals to P, which is the load that is acting over your gross area. You see it up here. All right. And that should be less than or equal to this. This is the adjusted stress after you go in the table and take out your value and apply the different adjustment factors. All right. For LRFD, it is F small fcu equals to pu. Remember know that for ASD they use P or PA, and for LRFD they use U, right? Because it's ultimate. And over the same AG, force over area equals stress that we know as a general thing, and it should be less than this stress. Again, this is the adjusted compression stress of the timber from the table multiplied by the different adjustment factors. Here we have the different definition where FC is the unfactored axial compression stress, as in small fc. P is the unfactored compression force applied on the wood column. A is the gross cross-section area of a tension member or compression member. They put tension, I don't know why. Again, we do find these errors in books because we deal with compression there, and they're talking about tension there. Class, you might want to correct that from now and put compression so that when you're reading, you don't. These things do happen. Remember that these books are written by you and I, by people, not by the creator. So expect to find errors. Just that we should be in a position to pick up these errors now with where we have reached in our career. Right, so this would be compression member, not tension member. All right. All right, let's continue. F prime C is the allowable compression stress, which is up here. And FCU is a factored height. From these, so these, the top part of it is really for the ASD, and the bottom part of it is for the, right? And they are saying tension again down here. All right. Now, it says here using the NSD or NDS, using the National Design Standards or specification, the books we have been using all along, adjustment factors applicable tables, table 3.1 and table 3.4, the allowable compressive stress parallel to the grain for the ASD and the LRFD adjustment compression stress are given as follows. All right, note it says parallel to the grain because we are looking at columns. Timber columns are going to have compression parallel to the grain. Timber columns. Okay, fine. So look, these are some timber columns. The image on my right here, right? Never mind these metal things, right? Those are just supports to keep the timber from going to the wet area, right? But these streaks that you see, these lines are the grains. So timber columns are oriented just the way the trees were grown, vertically. We don't try and cut timber where the column where the grains are perpendicular. No, only in beams loads act perpendicular to the grain of the element. For columns, it runs through the axis, so it's where the loads are acting parallel to the grains. All right, parallel to the grains. All right, so let's get back to this. Now for the ASD method, for allowable stress design method, these are what will be applicable. To arrive at F prime C, we take FC out of the table and we apply these modification factors or these adjustment factors for sawn timber. For glue laminated, these, because there are some things which are not applied for glue laminated. All right. I think I sent you something like this last week for beams. Now you get them for timber. All right. So for timber, for column, sorry, you'll be using these. All right. For sawn lumber, it's this from the table, the reference value multiplied by all these. for glulam column is reference value multiplied by all this. Under the LRFD, it's the reference value from the table times all of this. The last three being those designated for LRFD only. So like I said before, it's the same thing up top, but these now come because this convert, this is the resistance factor, and this is the time effect factor. Similarly, for the glulam, is reference value times all this like up here. And then this comes into play. These come into play because you're moving from ASD to LRFD. All right? And it gives out the definition of what each value means up there. All right? It says here where FC is the NDS tabulated reference design stress from this. We get them from these tables inside here. All right? KF is the format conversion from LRFD. It says here is 2.4 for compressive stress. So we know we need not to go and search for it. No, because it's 2.4. And 5C, which is a resistance factor, is a strength resistance factor for LRFD. It's 0.9 for resistance for compressive stress. We don't have to go and look for it again. It's 0.9. And lambda is a time effect factor for LRFD and is dependent on the load combination, right? And it says C table 3.11, right? For that value. The adjustments or C factors are discussed already in chapter 3 of the book that we use. And the column stability factor CP depends on the unbraced length of the column. All right. So there's a column adjustment factor, just like we have a beam adjustment factor, or stability factor rather, CL. We have one for columns also, which is CP. The higher the column slenderness ratio, KE over LR, the smaller the column stability factor, CP. For columns that are laterally braced over their entire length, the column stability factor, CP, is 1. Unfortunately, class, unlike beams, where we stick to the case where the beams are continuously braced or supported by flooring or whatever the case may be. For columns, we might not have that scenario enter, where CP is 1 by virtue of having a wall or whatever the case may be along the column. Not all the cases. So we are going to learn to calculate the value of CP, unlike the value of CL where we didn't, we use 1. All right? So we need to know how to calculate the value of CP, because our columns are not going to necessarily have any continuous lateral support. Columns do not always have that, because columns do not necessarily have walls on them at all the time. For the most part, our beams have roofs and floors to brace them. But columns might be internal, where they are stand-alone, they're independent. So we need to learn to calculate these. All right? So let's look at it. For ASD method, this is the expression for your column stability factor. 1 plus all of this. Over that, then minus that, all of that. And for LRFD, I don't want to read it out, it's all of that. Whereby all right, so these are what you use to find them. All right? And then to find these, you need to have these, which are given there, how to find them. See them there? All right? These are all those expressions with factor which we must use, must get married to. We're not interested in how they came about. We're just going to be using them. All right? All right, so this is for ASD. This is for LRFD. All right? Similarly, this is for ASD. All right? We know to get it from the value from the table already. We convert it to this by applying these factors, and that's for sawn lumber, which we mainly stick to, and these are for glue laminated members. And that's ASD. And for LRFD, similar scenario, where we have E min from the table and we apply these factors, right, for sawn lumber. All right, it says here, E min is the tabulated minimum elastic modulus for buckling and stability calculation and is a function of pure bending modulus of elasticity, E, which is a factor of safety of with a factor of safety of 1.6 is applied. In addition to a 5% lower exclusion value on the pure bending modulus of the fine. LE is the effective length of the column. Right? L is the unbraced length about buckle. Right? L is the unbraced column length. Right? So LE equals KEL. So we need to know what KE is because we can know what L is. L is the unbraced length of the column. Right? KE is the factor which we are now interested in. Right? It says Lx is the unbraced length in x-axis. Right? And we have Ly in y-axis. In this case, we have Ly1, Ly2, because based on this diagram we have right here, we have an intermediate brace in the y-axis. Remember, class, we have gone through this. Even though this brace is parallel to the x-axis, it does not mean it is bracing the column from bending in x-axis. It's bracing it from bending in y-axis, because bending in y-axis will take place like this, not like this. All right, and that is why Ly as Ly1 and Ly2, because it is braced in Ly. All right. Ke being the buckling length coefficient, and it's taken from table 5.1. Class, this table is not new to us. It's the same table we use when we're doing compression elements in steel. I do not think I need to go through it again. Right? It speaks directly to the support conditions of a column. Fix, pin, fix, fix free, pin, fix free. Again, is a different type of fix free. Right? When rotation is allowed. And this is a pinned fix, when it can move sideways. All right. Again, we have two types of values. We have theoretical values and we have recommended values. We prefer to use recommended values, even though if you use this value, then we're not going to kill you. But we prefer to use the recommended values, which is why it's called recommended value. All right. So that table is where we go to find the KE values. To apply to your L to find your LE. All right. So these are actually things that we have done before in steel. D being the dimension of the column section perpendicular to the axis of buckling. Listen carefully. D, dimension of the column section perpendicular to the axis of buckling. So if I'm checking buckling X, all right, fine. So let's read. For X axis buckling, use dx. D equals dx. For y axis buckling, use dy. Sorry, d equals dy. All right. The NDS code limits the slenderness ratio LE over D to 50 to minimize the impact of slenderness on wood columns. All right. Now, when we're doing steel, this slenderness ratio was limited to what? 100 or 200? 200 or 100, which of them? First, for timber, it's limited to 50 because they want to ensure that the impact of slenderness on timber is minimized. Timber is not as strong as steel. So we're not going to take the chance we took with steel when it comes down to slenderness, when it comes down to wood. When the slenderness ratio is greater than 50, the designer would need to increase the size and or reduce the unbraced length of the column by providing lateral braces, if possible, to bring the slenderness ratio within the limit of 50. It should be noted that the NDS codes allows slenderness ratios of up to 70, but only during construction. So during construction, slenderness can be up to 70, but for the final thing, it has to be less than 50. If not, change the size of the element, put in lateral braces. All right. C is an interaction factor, which is equal to 0.8 for sawn lumber, and 0.9 for glue lamp, and 0.8 for round timber posts. Give God thanks. We're not into posts and piles, so we don't have to look at these two. We might only be interested in these two only. FC asterisk is the unfactored crushing strength of column at zero slenderness ratio. That is strength when L E over D equals 0, which means excluding CP. FCR asterisk, which is for LRFD. No. Is LRFD adjusted crushing strength of a column at zero slenderness. That is the strength when LD equals 0, which means CP excluding. C is the interaction. This is for LRFD now. C is the interaction factor. 0.8 for sawn lumber, 0.9 for glue lamp, 0.85 for round poles, right? So the same factors from up by ASD. And KFST is a conversion factor. It is 1.76 for stability, all right? So right now we have, for columns, we have in KF values being given to us. We don't need to go into any table for KF. We have them right here. See them there? This is for bending. This is for compression. And this is for stability down here. So we have the KF values already given, and phi value also given as 0.85 for stability. All right. And ultimately, these are the compression stress checks. For sawn lumber on the ASD, it's given as this. For glue lamp, it's given as this. For LRFD, sawn lumber is given as this. And for glue laminated, is given as this. All right. No, so that is what it is for timber. For timber columns, it's similar to steel, except that we have to apply some factors to the stresses, but we need to check slenderness and find the critical stress for slenderness also, as in FCR. In steel, we call it FCR. It's called FCER or FCE in this case. Right? These are there. All right. Now, if we are seeking to design a column, just like we did with steel and concrete, it must meet the design criteria. It must meet the design criteria. The basic design criteria is that the axial compressive capacity of a member, it must be less than or equal to this. Right? The axial compression capacity of a member in terms of its nominal strength is Pu is equal to this. So the stress times the area. So this is what we should. This is really the basic equation and design of equation, or equation of design. All right. It says here for sawn lumber, the adjusted reference design value is this. We look at it up top before, and for glue lamp, it is this. We have looked at them before, right? Same things are happening again, but if we were to be looking at it from a design perspective, and these are the same thing again, but written in different format. See them there? So this is a check. This is really a check for the stability. Right? So this KL over D, which is the slenderness ratio check, must be less than or equal to 50. If not, increase size, put in some braces at the column. All right? So these are basically the same things, but from a design perspective. All right, we have gone through them already. Now, what is left for us to do is to put those theory into a practical application so we can appreciate it more. And I did think I put an example a column design example in the classroom for you yesterday. So you can open this and let us see if we can apply those basic knowledge, both from what we learned about stability from before and what we just looked at this morning, and see if we can appreciate how column analysis and design for timber is done. We're going to be looking at this as a compression member, and column stability calculation. And this is for the ASD method. All right. It says here, compare the axial compression capacity of a nominal 4x4 and a nominal 6x6. So we have two elements to compare. Post being used for an interior column only carrying gravity loads, right? Dead loads plus floor live load. Both members are number 2 Southern Pine. Right? So we change now from Douglas Tree Larch to Southern Pine and have a length of 10 feet. So both elements are the same length, carry the same load, but they have different cross section. One is a 4x4 inch, the other is a 6x6 inch. Right? Both ends are assumed to be pinned. Assume all members are loaded concentrically. That means loaded directly in their center. All right, so that means there's no eccentricity, there's no residual moment. Like just pure, it's pure compression that is. All right. So here we are, class, with a column of 10 feet natural length. All right. It says that the ends are pinned. So let's represent that. They have this arrow, but I prefer not to have an arrow there. I prefer to have the support that you guys are accustomed to. Just look like that. I'm going to change the color so that you can appreciate even more. Yeah, all right. I'm almost sure that sometimes they have something like this. All right, so it's pinned. Pin support. We're using that symbol to replace the original red arrow we have. Let me get rid of the arrow. All right, fine. So here's our support. And I'm going to do the same thing up here. You can appreciate even more what we did. Let me group this. Let me copy this and paste it. Okay, so it's pinned. All right, fine. So you can do that. All right. That way you can relate more to what we do. We talk about pin. All right. So let's begin. First thing we're going to do, we're going to start with the 4x4. We're going to look at the 4x4 first. All right. Remember now, it's number 2 Southern Pine. Number 2 Southern Pine. We're looking at compression, so we're going to take out the stresses that are important to compression. All right. These are the only important. We don't look at no bending. No, we don't want to shear. We want FC, E, and E min. So let's go into this book, into the supplement. Right. We're going to be looking for Southern Pine, and we're looking for dimensional number, SON number. So this one says all species except Southern Pine. So we need to get ourselves out of that table. All species except, so we need to get out of that table. All species except Southern Pine, so we need to get out of that table. And this table is now saying Southern Pine. So table 4B. All right, Southern Pine. And it says 2 to 4 inches thick. So we're looking for 4 by 4. 4 wide, 5 to 6 inches wide, 8 wide. We're looking for 4 by 4. And not only that, we're looking for 4 by 4, and it must also be number 2. Number 2 southern pine. All right, so the number 2 southern pine. Number 2 southern pine. 2 to 4 inches wide. Size classification 4 inches wide. So it can't be any of these, right? Because these are saying 8 and 10 and 12. These are saying mixed southern pine. These are saying southern pine. These are saying southern pine. All right. So it can't be anything down there. It can't be anything down here because this is a mixed southern pine. We don't need that. These are saying southern pine, but they're saying 2 inches and wider, 2.5 inches and wider, 2.5 inches to 4 inches thick. These are not what we were looking for. Number 2. So we are stuck with up in this table. Not here because it's 4 inches, 12 inches. Not there, 8 inches, not there. So let's look in this. It says 4 inches wide. But if we look at this, it says construction standard utility, not there. So we need to find number 2. Number 2 southern pine. We are inside here. Number 2 southern pine, this one. Let's see if we're correct. Number 2 southern pine. 2 to 4 inches wide. I'm looking for compression. This one. So if I go, is it third from the bottom? 1, 2, 3. Third from the bottom, 1, 2, 3. And I say 1,450. Let's see if we have it correct. 1,450 psi. All right. Are you following, class? Class?
Yes, sir.
Are you following? Did you see how I narrowed down to find the element? It's a 4 by 4 post. Number 2, southern pine. So we have to ensure that we're in the correct table. That's number 1. Southern pine. Right? We're looking for 4 inches wide, which cannot be in these because they're saying 5 to 6, 8, and it gets larger. So we're not interested in anything down there. We are stuck it up in this area, 2 to 4 inches wide. But which one do we want? It says number 2. Be careful now, not to just choose a number 2 because we have number 2 dense, number 2 alone, and number 2 non-dense. It just stated number 2, so it has to be this one, and that's why I choose this third from bottom, and we're interested in only this FC and these 2 E's. All right, so it's 1,450, which is this one, is 1.4 million for E and 510,000 for E min. So let's see. 1.4 for E and 1.5 E min. All right. So those are the stresses that we need to go in the table for. All right. And it says table 4B. All right. Now, from the same, let's look at why we take size factor CF. Let's go back to what we did earlier. Because we'll be needing CF, we'll be needing CD, CM, CT, CF, CI. We'll be needing all this. That is why they have gone and take out CF. Right? These are our guides. If we use these all the time, we know exactly what adjustment factors we should be looking for a particular. It happens to beam, it also happens to columns. All right? So we're looking for CF. Now they say that CF equals 1 from table 4B. The same table 4B class that we just used a while ago. This is table 4B. This is table 4B. But before the table, the page before the table, we have these. See the CF, appropriate size adjustment factor, have already been, right? And if we read this, if we read all this, we will know how to arrive at our CF, right? They're saying that CF equals 1. Let's see why equal 1. It says appropriate size adjustment factor have already been incorporated in the tabulated design values for most thickness of southern pine and mixed southern pine lumber. We are in southern pine. For dimensions, dimension number 4 inches thick, 8 inches and wider. All grade except dense structural dense FB shall be permitted to be multiplied by a CF factor of 1.1. For dimension number wider than that, all right, so we for dimension number 4 inches thick, 8 inches and wider, so 4, 8 and wider, all grades except dense tabulated C FB shall be permitted to be multiplied by a CF factor 1. There is in 1.1. Sorry, there is in 1. Well, this is saying 1.1. Okay, this is saying 1.1. I'm seeing a value of 1 for the calculation. Not too sure why. I would have gone for a 1.1 because that's what the narrative says. All right. CM, which is moisture factor, table 4B again. This one, table 4B. They are using 1. The question didn't say anything about moisture. It says here when FB times CF is less than that. All right, so we had done this last week, right? Apart from having these, when we come in the table and see these asterisks, that means we have to do some further checks. All right. For CM factor, right, we are interested in FC because we're looking at compression parallel to the grain. All right. So in the table, if we come to the table alone, we see it's 0.8, but that 0.8 also comes with 2 asterisks at the side. It therefore means there's something special about that point, that value. What it says is that when FC is less than or equal to 750 psi, CM equals 1. When FC is less than or equal to 750 psi, CM is equals to 1. Let's look at our FC. But our FC is more. Why is it still 1? Our FC is more. Unless there's something that we are missing. Are you seeing that, class? Are you following? Class? Class? But no answer. Class, are you still there?
Yes, sir.
Right. I'm saying that by this table, the wet service factor for compression parallel to the grain, it have a default value of 0.8. But that default value attracts other conditions. It has two asterisks. Therefore, means I should go where the two asterisks are. And it says here that when FC is less than or equal to 750 psi, the CM should attract a value of 1. Our FC value is 450 psi, which is not less than 1. But there, which is not less than 750. It is actually more. But they are still using CM equal 1. While from my analysis right here, our CM should really be 0.8. Do you agree with me, right? It should be 0.8.
Yes, sir.
Based on this, it should be 0.8. It should be 0.8, but they're using 1. Right? Don't know what the reason is. I don't know what the reason is, but they're using 1. For temperature, CT equals 1. They are making everything 1. CT equals 1. Let's look and see what the temperature things speak to. CT, CF. Right, so CT is found elsewhere. CT is found in the NDS
Table
table 2.
2.3.
Okay, your phone, right?
Yes.
Not in the supplement now. Good thing about this example, it tells you if it's a supplement or the table or the book itself. So you have gone to NDS table 2.3.3, right? The NDS, this is the NDS now, not the supplement. It says 2.3. All right, fine. 2.3.3. Table 2.3.3. It's a I. Okay, fine. So I'm on the table 2.3.3, and we're looking for compression. Okay, fine. So if they're saying that the temperature is less than 100 degrees Fahrenheit, they did not state that. So it might be an assumption that it's less than 100 degrees Fahrenheit. And even if it's wet or dry, it doesn't matter. The factor is 1. Only if you add extreme temperatures like these, it will be different. But let's say that it's normal temperature, which is what I assume they're using up here. It did not state it. Assume it's they did not state it, but I'm going to assume that is normal temperature because this is used within a building, really. So let's say that it's normal temperatures. So that would be 1. I don't want to be wet or dry. It's internally shouldn't be wet. It should be dry, really. So the factor is equal 1. CI, incision factor, that's taken from 4.3.8. It didn't say anything about incision, really. But multiplied by a factor of 1 shouldn't change anything. But let's look at the table in the NDS. It says table 4.3.8, 4.3.8, table 4.3.8, that is all the way down 4.3.8. Something I want you guys to learn to do. Having to scroll and find about 4.3.8 should be anywhere now. Table 4.3, 4.3.1, 4.3.8. Right, fine. So this is incision factor. Let's see what it says about incision. It says references and value shall be multiplied by the following incision value CI. When the dimensional number is in size parallel to the grain, depth of 0.4 inches, a maximum of length of 38 inches, a density of incision up to 100 per square foot. Incision factor shall be by test or by calculation using reduced. All right, but incision factor, that design value. We should be looking for FC, which is 0.8. He didn't say anything about incision. There's no incision really. So if there is a value of 1, it changes nothing. If there were incisions there, then this value would have applied. So to put a value of 1, change nothing. All right? Change nothing really. Now we have buckling stiffness factor. This is stability factor now. Buckling stiffness factor. All right? Buckling stiffness factor is table 4.4.2 in the NDS. The same book we go a while ago. So it's 4.4.2. So we are going even further into this book. 4.4.2. Stability members, buckling. Where's that table? 4.4.2. Is that a table?
It's not a table, sir.
Huh?
It's not a table.
Oh, is a clause?
Yeah.
4.4.2. Where is that now? 4.4. This one.
You're right there.
Okay. Wood trusses. Increased cord stiffness relative to axial loads where a 2x4 or smaller sound number, no? So that does apply to us. That doesn't apply to us. Where does it apply to us? Again, this doesn't apply. Column of compression cord. That doesn't apply. Okay, fine. So this is our calculator, right? But let's leave that until we do the other things. Load duration factor, CD, and that's NDS table 2. NDS table 2.3.2. Okay, fine. So load duration factor is dependent on the load. We have 2 loads, live and dead load, right? So the live load, and it says you should use a larger factor. So the live load is going to dominate. So it's table 2.3.2. So all the way back up. We have to come back to that stability factor. 2.3.2. 2.3.2. Okay, fine. 2.3.2. Right, fine. So load duration. Okay, fine. So it's occupancy live load. This one. Because we only have 2 things. We have dead load and live load, right? So it's occupancy live load. And there's claim it as a duration of 10 years cumulatively. So the factor is 1. So if we were to compare this and this, it says I should use a larger one, which is 1. And which is why they had used 1 as their CD right there. All right. After that, it's a matter of applying these factors to the stresses based on these. So we have the F and we have the E. Let's look at what the E had asked for. See them up here. And we're doing this. So the E for sound lumber are for CM, CT, CI, CT. So it's CM, CT, a small t really, CI, and CT, big T. All right. So if I should crop these and carry it over there just to compare, and they have gone for that. So let's look. Let's make sure. Okay, fine. So let's go now. E prime min, which is down here, is equals to E min, CM, CI, CI. Perfect. And for E prime by itself, let's see what the let's see what is required. I have E min and E prime. Let's go down further. Oh, what? Let me look at this one. This one is not appearing. All right. So this I'm not seeing in the narrative. E prime. But will you take it out though? To be E. So it's E times all that to give that. All right, so let's continue. We'll accept this. I'm not finding the expression in the narrative for that. All right, but we'll take that. All right. Now remember, now we're looking at nominal size timber, right? So even though it says it's a 4x4 up here, it's all just lumber. So it doesn't mean that the timber is 4 inches by 4 inches. The actual size is this: 3.5 inch by 3.5 inch, which is what they actually is spelling out here for you. So note that. Similarly, the 6x6 won't be 6 inches by 6 inches. It's going to be 5 and 5.25 or something like that. All right. So with this, we're going to be finding the real area, which is 3.5 by 3.5, which will give this. All right. KE is equals to 1. Why is KE equal 1? Who can tell me what is KE and why is it equal to 1? What is KE and why is it equals to 1? Class? Because both ends are pinned. All right. And so what is KE again? What is KE? What's the definition of KE? KE class is the buckling factor or the effective length factor. Let me find it again. KE, buckling length coefficient. All right. Because we're in pin scenario, both the theoretic value or the recommended value is equal to 1. All right. And that is why that one quickly jump out from them. All right. Length L. What is the L? It is for our element, it is 10 feet. 10 feet, and that converted to inches is 10 feet by 12. That's 120 inches, and that's where this 120 comes from right there. All right. So if K equals 1 and L equals 120, then KE times L, which is equal to LE, that's equal to 1. So the effective length is equal to 120 inch. Nothing changed about it. All right. Because it is a square element, no brace nowhere along the element. That means buckling in both axes is going to be the same. And that is why they're not saying KER and KEX and KEY or LEX and LEY. It's the same thing. And that reduced to the slenderness ratio, effective length over D. D being 3.5. So if you divide 120 by 3.5, you get 34.3. That should be compared with the 50. Because it is less than 50, then it's okay. All right. So we can add this like this. Less than 50. Less than 50. So, okay. One right to right, so buckling is okay. It's not slender. All right. That is what took place right there. It's less than 50, so it's okay. All right. So we can move on. It's not slender, so we can move on. Column stability factor. Having found that now, we can move on to column stability factor. These now are coming out of what we did earlier on this morning. This narrative, column stability factor, CP. CP equals to this one. CP. We're going to now apply this expression, but we're doing it by piece. right? This expression needed all of this. So they do them piece by piece so that they can put it in there, right? So this, we already have this. Now we already have E min is E prime min because we have already calculated it up top. E prime min this. So it's a matter of plugging that value into this. We have LE over D because we just calculated LE over D a while ago. All right. So we need to square it. And then somebody doing that. If we should put this value, this 5.1 times 10 to the fifth, right here, and do all this, we should come out at this. That's critical stress from Euler. All right. Then we also need this because this comes down here. So we can now do this, putting all those values, all of this that's applied, the one that are applicable. We can put those, everything is one anyway, based on the thing 1 1 1 1 1 1. So nothing changes, it remains at 1450. It remains at 1450 because everything here was 1. Apply a C value. Remember what C is? They are defined C for us to be that look C, the common C. In the narrative, C, when you find CP, C means something. We'll go again. Pure tension, compression. After we go there, then we go to this. All right, and little C meant something. Right, fine. C. It says C is the interaction factor. It's 0.8 for all Son number. 0.8 for Son number. And that's where this 0.8 come from. Because this is a Son, it's the cut number, Son number. Alright, so that's where that come from. And after that, it's a matter of putting this value, and this value where they apply. And obeying the rules of subtraction and simplification and all that. And it should come out at this. Right? It should come out at this. And this now becomes your column stability factor. Right? Column stability factor. Which you will now apply to your stress factor, the stress to get the buckling stress. So this is actually the buckling stress. Again, all the factors which apply and joined by the CP. So it's the same thing as above, but this time it have an asterisk right here because there is no CP to it yet. Right? When CP comes to it, ultimately, if you look at it, it's the same thing, but CP is a part of it now, and that is now the strength of the column at buckling, the stress really. So this is the buckling stress of the column. So if we know the buckling stress of the column, we can now find the buckling load of the column, the buckling capacity, by multiplying the stress by the area. That is what this up here was saying when it says column design. I want to go through all this so that you can, when it says column design, where is it again? It's in the narrative, anything I sent you. This, see here? Axial compression capacity of an element. This. PU is equal to that. So that is what this speaks to. It's a matter of multiplying this stress. And the same thing we did with steel. Multiply this stress, we call it F critical for steel, by the area, the gross area. All right? Which is 3 by 3.5 by 3.5 from up above. The same 3.5 by 3.5 up here. This. And that will give us the load it can carry. That is 4,120 pounds. It says pound foot. Oh, sorry, pound force. It's pounds, right? Because this is PSI, and this is in area is going to be in inch square. So this is inch square. You're going to come out at pounds. All right, pound force. So be careful. This F. I think it means something. It means pound force. All right. This though we can compare against the loads acting to see if it can. But in this case, we did not have any load acting. So we are merely finding the amount of load it can carry. That's all. We didn't get any load up there. So that column at 4 inches by 4 inches can carry a buckling load of 420 pounds. Right? They have actually gone also and checked bearing. What is bearing? Let's go back to what we did in steel. When we did steel columns, we check for two things: for buckling and for yielding. This is the same thing as yielding. So buckling will mean buckling, and this is yielding. This is when we use Fy times Ag. This one. For steel, we use Fy times Ag, the yield stress times the gross area of a section. And then we check buckling, which would be all of this. So it's a similar thing, really. It says actual compression stress parallel to the grain, assuming column loaded to 100% calculated buckling capacity. So let's see what I did here. This bearing capacity is actually taking this stress. Where is it? F prime C. This one. But you can take up there. And applying 0.75 to it. Remember that small FC, this FC class this would be if the element had loads that we calculated F prime C from the loads. But because we don't have any loads now, we are saying that this column can carry this stress. Right? Now, this is really applying a factor of safety. A 0.75. Right? It says if F prime C is less than that, so bearing parallel to the grain is okay. If F prime C is less than 0.75 FC, so no rigid bearing insert is required. All right. So let me explain what bearing inserts are. If a timber element is tending to crush, then they can actually insert some bearing elements at the ends of it. Which way they call it insert. Well, I'm not too sure if Jamaica have a capacity to insert them. It's actually some local steel inserts, like plates. Let me see if I can find one online to explain what bearing inserts are. Timber bearing inserts. Timber bearing inserts. Timber bearing inserts. Timber column. Timber column. Bearing inserts. Okay. So all these are bearing inserts. Remember, I showed an image earlier. I said, never mind the metal thing. These are like bearing inserts. It therefore means that you don't want the timber to be Perfect. Here's one. Don't want the timber to be bearing directly down on whatever the support is. So you put some metallic inserts now so that the bearing is shared across a metal plate as opposed to just timber. Right? We don't have that luxury though here in Jamaica so much. So we might not get down to all this. We might not get down to all this. All we know is that we would stop right here. For buckling, which is more critical than bearing, really, the element can't carry more than 4,120 pounds. All right, that's all we know. That's it for the 4x4. If we look at the 6x6 and carry out the same exercise class, and they're just putting 2 right here because they are saying that the element 2, right? So never mind these little 2s down here. It doesn't mean anything but saying that the element, we're looking at element 2, right? The same basic operation, except that you have gone for 6x6 column, 6x6 posts in the book, and let me do that for the benefit of those. So we are on Southern Pine. Remember, we are on Southern Pine. I'm looking for 6 inches wide. So we are in this. We are in this, and we are what member again? The member is what? Number 1 or number 2? The element is number 1 or number 2? Number 2? No. The element is what? And number 1 Southern Pine. Let me quickly look back at the element. It's a number 2 Southern Pine. So again, we'll go in this table, and it's number 2 Southern Pine 6x6. So we should be looking at values of FC, third from the bottom. 1, 2, 3. 1,400 PSI for compression. 1.4 million for that, and 510. So the values seem to be the same thing as we used before. Let's get back to it, right? Now, FC2. Now let's get back in the table. It's a 6x6 Southern Pine. 6x6 Southern Pine. Southern Pine 6x6, number 2. Now, but the values should be these. So they have an error there. These values should be coming from this, number 2 Southern Pine, and it's F prime is FC this, which is 1,400. Not 565. 1,400. They are 525. Where did they get that from? Table 4D. They said table 4D, but why 4D? Let's look at what in table 4D. Oh, class. So this is discovery. There's a separate table for timber elements 5 by 5 inches and larger. So that 6x6 actually falls within this table. And there's no stipulation here to say whether it's pine or not, because in this table there is Southern Pine, I imagine. Northern White Oak, Red Oak, Southern Pine, right? Southern Pine. So it's number 2 southern pine, 5 by 5 and larger. So 6 by 6 falls within this. So if I go across the fourth element up, 1, 2, 3, 4. Okay, fine. So this is it. So it's 525, 1.2, and 440. 525, 1.2 mil, and 440,000. So it's 520, 122, and 4. Right. So we have to be careful how we use these tables. Because the table before, that's 4B. 4B was actually saying 5 to 6 inches wide. One would be inclined to think that they could take something from inside here because it meets 6 inches. However, they are saying that they have a separate table for 5 inch by 5 inches and up, which is what they use, and that's table 4D. So that's what they use, table 4D, but for this 6 by 6 case. All right, and again, these applicable values would have been coming from wherever they come from. These tables as they are quoted there, as they referenced there, and the calculation remains the same. Everything we did up top above would have been done down here. Nothing changed about the length. Nothing changed about the length or the KE. What will change though is the slenderness ratio because D is larger. So this becomes smaller. If this becomes smaller, then the critical stress actually is larger, should be larger, and the capacity should be larger really. Look at the capacity now. Should be larger. And that's logical. That's logical. If you have the same material, the same southern pine, same length, same end conditions, the larger you go, the better off it becomes. And that's what design speaks to anyway. If a small one didn't work, we would have been increasing the size. So we only increase the size because we expect the bigger one to be better off. So the comparison really is that the larger one will have a larger resistance to buckling than the smaller one. Let's see what the question was really asking for. The question asks us to compare the axial compression capacity. All right, so the larger element has a larger compression capacity than the smaller element. Like I said again, that's really logical. That's logical because nothing changes. It's not like one of them is 14 feet and one is 10 feet. Both of them are 10 feet. So the same conditions, just the cross section different. So the bigger one is going to have a larger resistance or larger capacity. And that's what really happens. If you were to look at it from a bearing perspective, they are saying that the bearing, you would need bearing capacity for the larger one. Bearing plate, really. But we are not interested in this bearing plate thing. Like I said, we are not privy. No hardware in Jamaica is going to sell that. It's really one of the drawbacks. Why we're not so much into timber construction and timber design, because we do not have all the necessary accessories. We don't have the joist hangers, the connection plates, and all them things. And let me show you what joist hangers are while we speak. Joists, hangers. These things. You see all these things? We do not just stock them. Yeah, see them there? So, which is why timber construction is not really as popular here in Jamaica as it is elsewhere. Because we don't have this. So we are going to be dependent only on simple nail and screw, which of course is not as effective as all this. So all these inserts and base plates and bearing plates, we might not have them. The typical in Jamaica is for a man to just put a concrete base and put the timber in it. A lot of our timber columns are actually either they placed on top of a slab inside the building, or if or they're placed in a concrete, mass concrete pad footing. And over the years, it just stayed there on the foot of it. The base of it deteriorate because of moisture. And that's what happened. We don't really have all these fancy inserts and so nobody's gonna sell them. And you can't wrong the hardwares because if people are not using timber that much, why buy something from overseas only to have it there on your shelf for decades, not being sold? Right? However, because we're engineers, we need to learn to design not just concrete and steel building, but also timber building. Hence, we have done the timber design for beams, simple beams, and simple columns. All right. And with that class, it really sums up, for the most part, what you are expected to know in timber design